cost pressure, I think, is going to drive innovation. But second, I think we as a community are really using, in some sense, a lot of the traditional AI work that's been done today has been done on traditional general purpose infrastructure. Those processors are suitable, but they're not optimal for this work. At Cerebras, we've built a completely new class of processor that's built from the ground up for AI.
Hi, Natalia and Andy. Thank you for joining me on the show.
Happy to be here. Thanks, Richie.
Excellent. So we've seen a ton of, quite frankly, dramatic progress around generative AI in the last 6 years. So do you see this dramatic progress continuing much longer? Natalia, do you want to take this?
Oh, yeah. I think we are just starting. I think there is still a ton of both advancements in fundamentals, how generative AI models can be trained, how we can make them more efficient. But also, I think we're just tapping into what those models can do. There is a lot of excitement these days around, I'd say, educational and entertainment use cases. So all of us probably have tried using ChatGPT, looked at image generative models. But in terms of how all of those models can be realized in real life use cases, I think there is still a ton of discovery to be made, and it will drive requirements of the models, and it will drive a lot of additional progress, both in training those models and also on applications.
Okay, that's interesting. So it's really going to be the wider adoption of use cases that's going to drive the technological advancement. Okay. And Andy, do you have a similar take on this, or have you got a different opinion on how progress is going to go?
Very similar take. I think we're just scratching the surface. I found myself reflecting as Natalia was responding. Imagine where we were with, say, computer graphics 20 years ago and where we are today with rendering and gaming. I think we are today with AI maybe where we were with graphics or analytics 20 years ago. I think there's a huge proliferation of applications brewing right now in both enterprise and research. And I think we're just at the beginning of understanding which ML techniques and network architectures and data types are the most amenable. So I'm thrilled to be where we're at, particularly at Cerebras on the AI computing side, but I'm really looking forward to where the field is going over the next 1 to 2 to 10 to 20 years.
That gaming analogy is kind of cool. It's like we've just reached the sort of PlayStation 1, Xbox era. And it's like, wow, stuff's in 3D and it looks really cool, but like you can't imagine what, PlayStation 5 looks like.
Yeah, absolutely. We make this analogy pretty frequently, but Cerebras is well known as an AI computing company. We spent a lot of our time focusing initially on software support and our hardware systems for training, but particularly around large model inference. We make this analogy that I think we're in some sense in like the web dial-up era of inference in particular, where today we're in that the moral equivalent of that dial-up era where we're waiting for the modem to dial up before we get our answer, but we're not yet in the modern day network equivalent of like instant responses. So I think both in terms of the technology and the applications, both on the training and compute and inference side, we're just scratching the surface, man.
Okay, yeah. I think nobody really misses that modem dial-up noise where you're waiting for things to load.
Exactly.
Yeah, so hopefully we get broadband soon.
That's right. Yeah. It's coming.
Nice. So lots to be excited about. And I think one of the sort of caveats is that as a lot of generative AI is starting to get put into production, people kind of go, well, actually, it's kind of expensive at the moment. There's a lot of costs around just running these models, doing inference, like beyond trying to train things yourself. And so do you think these costs are going to affect the development of future LLMs? Andy, do you want to go first this time?
Yeah, happy to. So I think, look, a couple of things are going to happen. First of all, cost pressure, I think, is going to drive innovation. But second, I think we as a community are really using, in some sense, a lot of the traditional AI work that's been done today has been done on traditional general purpose infrastructure, and that's one of the big cost factors in innovation, right? So people are building models on large clusters of small general purpose processors. Those processors are suitable, but they're not optimal for this work. At Cerebras, we've built a completely new class of processor that's built from the ground up for AI. And as a result, it's faster, but it's also more efficient. So that means that if you're, say, training a model, right, you can go an order of magnitude faster than you could on an equivalent GPU system. And it's going to be more efficient, not only in terms of developer iteration, being able to test more ideas per unit time, but it's also going to be more power efficient underneath the hood. And then I think given that right infrastructure for AI research, researchers are going to build not just larger models, but they're going to build models that are more efficient and use more efficient methods like sparsity. And given the right processor, you can harness those advantages and turn those sort of natural advantages, say a sparsity in a neural network, into performance advantage and cost savings. A practical example of this, and it's something that we're pretty excited about at Cerebras in the very near future, is AI purpose-built hardware for inference. And we're launching inference, and just as a sort of data point, right? Our inference is going to be 20 times faster than GPU, opening up new applications, but it's only going to be about a third of the cost, right? So given the right infrastructure and new methods, I think cost pressure is going to drive innovation, but the right infrastructure is also going to make it more accessible.
Okay, so that's cool that you're not just going for let's try and help the developers. It's also going to be like let's bring this to a sort of wider audience. Now, it seemed like there's sort of two levels here. So you've got the hardware level. You talked about having custom chips rather than GPUs, and then there's also some of the software techniques. I'd love to get into both of these. So maybe we go with hardware first. So what makes these chips different from a GPU?
So I never leave home without it. I happen to have one here with me today. I don't know, but this is obviously a unique chip, right? At Cerebras, we approached the problem of AI compute from first principles. And what I mean by that is we actually looked at the workload of neural network training and inference. And we asked, okay, what kind of compute operations, what kind of precision, what kind of communication, memory, access patterns does this work have? And we built our processor around that. So obviously this chip is big, right? Most computer chips are the size of a fingernail or postage stamp. The chip that powers our system is the size of a dinner plate. We call it the Wafer-scale engine because it's the scale of a full silicon wafer in chip fabs. It's about 8.5 by 8.5 inches on an edge. So how is this different from a GPU is the question, right? And it's not just because it's bigger. AI compute requires massive computation, sparse tensor-based linear algebra operations, and the ability to handle data in motion, so high communication bandwidth and high memory bandwidth. And that's why we built our Wafer-scale engine the way we did, and it's what the Wafer-scale engine is best at. So this has 900,000 cores on one chip. They're all designed from the ground up for sparse tensor-based linear algebra operations, mostly at lower precision because that's what AI compute wants. And all those cores are directly connected to one another on the wafer. And there's 44 gigabytes of all on-chip SRAM, like a L1 cache. So lots of memory close to compute, and the compute can talk to each other very quickly. So all those attributes of AI computing that I talked about, that's what this thing is built for. And it's fundamentally different than a legacy general purpose processor that's small and far away from memory, like a GPU.
Okay, so really, because you're not having to solve many different problems like a general purpose GPU is, you can focus on just optimizing for just these sort of linear algebra operations that are needed by the neural network.
Bingo. Yeah, and the result is, order of magnitude faster on both training and inference, depending on the workload, and more efficient and easier to program. And that sort of trilogy of benefits all acts to accelerate innovation and accelerate compute on the inference side for models in production.
So you mentioned a few sort of ideas around how large language models can be done better from a sort of design, like the neural network architecture point of view. So maybe let's get into some of those. The one you mentioned first was sparsity. So Natalia, can you talk me through what is sparsity in a neural network and why would you want it?
Yeah, sparsity, in general, sparsity is when you don't have all of your weights being non-zeros or activations. So sparsity is when some of the elements of your matrices are zeros. It doesn't matter which matrices are there. So when we're talking about sparsity as it's applicable to training of neural networks, how it can help you, it can reduce computational cost, and it can reduce also memory requirements to run inference or to train these models. And I think overall in community, there is a broad acknowledgement that sparsity is one of their avenues to make training more efficient, to make our models less expensive to train and to run inference with. And there are several approaches how you can implement that during your training or during inference. So you can think about activation sparsity. Essentially, when you train a neural network, that's always interaction between the parameters of the models, the weights, that's one of the matrices that participates in this computation, and data or activations, that's the second argument, and they like combine together you do essentially multiplication and some linear operations on top of that. So you can think about inducing sparsity or making sparse either one element or another, and you can take advantage when you do either of those. And there are many methods there which allow you to, again, reduce cost of compute and reduce memory footprint if you induce zeros in your model parameters. Bottom line, throw some zeros either into your weights or into your activations. With that, reduce the cost of computation and reduce the memory footprint.
All right, nice. So I guess the idea is that the weights of each of the neurons in the neural network, that's some sort of measure of like its importance. And if it's sort of quite small, you can just pretend it's a zero, and that lets you ignore it effectively in some calculations. Is that right?
Yeah, if you think about the whole process of training neural network, you're starting with the huge pool of parameters, and it's very well known that all of the current neural networks over-parameterized. So we throw way more parameters than it's needed to actually solve the problem. And then the goal of the training is to understand which weights should be large, so essentially which weights are meaningful, and which weights are small, they don't bring any value. So just if we can figure out how to do not train those smaller weights which don't bring any value from the get-go, it would be better off.
So it's just a way of sort of simplifying the computations for bits of the neural network that you don't need. You just sort of ignore them. Okay. And then the other aspect was about using sort of smaller numbers, this idea of like quantization. So can you just talk me through again, like what does that mean and how does it work?
Yeah, that's another approach how you can reduce both compute cost and memory footprint for your model is when you use lower precision to represent either weights or activations in your model. So you can think, if you recall your course for computer science, every single number that you can represent and the computer can read can be represented at different precision and can take a certain number of bits. So you have single precision, double precision, half precision, 4-bit precision, 2-bit precision, maybe binary, and you just have zeros and ones. And less precision, less precise your computation is. So with the numbers with less precision, you can represent smaller range. So you can do only certain number of numbers and also smaller precision. So how much resolution you get for each of them. If you go to lower precision, again, it takes less space in your memory and it's also less expensive to compute, but it's less precise. So there are a lot of approaches how to make training of neural networks work with lower precision. Today, when you train large language models, you typically do that in mixed precision. People typically say half precision, but in reality, you still have to have some operations in single precision, 32 bits. But there is a lot of research going on how to make it stable at lower precision. And people have figured out much better how to reduce the precision of weights after the model has been trained. So let's say I've trained my models, I have all my weights in half precision. Now it's much more clear how to reduce precision of those trained weights without huge impact on accuracy and allow cheaper serving and cheaper inference.
Okay, so that's interesting. So you train with bigger numbers, these half precision numbers, and then afterwards you say, okay, well, maybe some of these values we can sort of shrink them even more because we don't care about the precision in this area of the neural network.
Yeah, one additional caveat is to actually take full advantage of all of those. From the theoretical or algorithmic point of view, sparsity is great, quantization is great. But to take advantage of all of those in real life, you need to have also hardware which is capable to work with low precision numbers, and the hardware which is capable also to work with those sparse tenders. And that's a very also important notion to keep in mind.
Okay, interesting. Yeah, so you need to make sure that the hardware supports what you're doing with this. And Andy, I think you mentioned before that the Cerebras chips, they're designed to work with lower precision numbers. Is that correct? So it's designed especially for this kind of neural network problem.
That's exactly right. So as Natalia mentioned, with sparsity, most of the data and most of the trained models that exist have a lot of zeros in them. And on a traditional compute platform, like a CPU or a GPU, when you run the model, usually what you're doing is you're doing multiplications and additions, right? And a traditional dense compute platform like a CPU or GPU, in particular GPU, will take that zero value and will actually execute the multiply by zero operation. Right? So it takes time, it takes compute cycles, it takes power. But we actually know what the answer to multiply by zero is. And so if you had instead a hardware platform that could, say, detect those zero values and just avoid them and move on to the next non-zero value, you would end up accelerating the compute and saving yourself power. And that's what the Cerebras platform does. So we sort of acknowledged in the design of our hardware that the nature of the compute workload involved a lot of zero values. And so we built that in so that we can actually take advantage of that, and our users can take advantage of that natural aspect of the data in neural networks. Similarly, on the precision side, we support in our hardware today 32-bit, 16-bit, and 8-bit numeric formats. And so we're really in the sweet spot of the numeric representations that are common for both training and for inference. And we can execute those at massive performance advantage over traditional machines on both the training and the inference side.
Okay, so yeah, it's very convenient that you multiply any number by zero. The answer is going to be zero, and you can do a little shortcut there. Okay, nice. So I'm curious, are there any other techniques that are used in order to make large language models more efficient or more performant?
Yeah, I think we've discussed a couple of those. So using sparsity and the different types of sparsity. So remember I talked that you can introduce those zeros either into weights or into activations. Just activation sparsity or weight sparsity. There are also different techniques on how regular those zeros are among the weights. So we can talk about structured and unstructured sparsity. Maybe some of you have heard about models called the mixture of experts. That's a perfect example of models with structured block sparsity. Yeah, I think for all of those techniques, the goal is that if I have a certain budget of compute, how can I get to the best accurate, the best highest quality model given that amount of compute? And it's been shown that with sparse models, you can get actually to better models by spending the same amount of compute compared to what you would potentially get with dense models. Mixture of experts is one example of those structured sparse models.
Yeah, do you want to just talk us through like how mixture of experts works?
So mixture of experts, it's when you hear mixture of experts, maybe you think about the common approaches which have been in the past called ensembles of experts. When you have completely separate models, you have completely different experts or predictors, and then you take a vote and decide what the accurate answer is. Mixture of expert model is not exactly that. So you still have those experts, but they are built into a single analytical model. And from the computational point of view, when you train a model, usually with a dense model, you have every single data point to influence every single weight in your model. So you need to make computation and see how those two react to each other for every single pair. For mixture of experts, it's an example of weight sparse models. So you still feed all of your data points through your model, but you do not get all of the model weights interact with all of the data points in your training data set. So the model selects, okay, this batch of data, this number of training examples, they will only influence this partition of the model. And that next set of examples will influence and will change the values only of that partition of the model. With that, you can remove this all-to-all dependency, and only a subset of the weights get to be influenced by certain data points. And that's what's reduced the computational cost at the end.
Okay, so I guess rather than having one giant large language model, if giant and large go well together, I'm not sure, but you have a few smaller models that are essentially, I guess, glued together. Does that sound about right?
No, I think it's not. You still have this large and giant model, but you don't have all parts of the model to take inputs from all of the data points. So the model is still the same, but the model decides inside that model, I will look, every single part of the model will look only into some parts of the data. So not all parts of the model are created equal, I guess. So, and that's what makes like why people call it mixture of experts, because you can think those parts of the models being different experts, and they only responsible for reacting to certain data points. That makes sense?
Okay, so you got one model, but just different parts of the model are responding to different kinds of inputs.
Yes, to different kind of inputs. Yes, that's exactly right.
Yeah. I'm gonna go out on a limb here because I'm really enjoying this conversation, but I'm gonna go out on a limb with potentially a really bad analogy. But I keep thinking in my head of like an octopus, and I can imagine like a prompt, so like an input comes into the octopus and comes into the head and the brain, and that does something, and maybe it only needs one tentacle to respond, right? And so input comes in, only needs, even though it's got 8 tentacles, the model is still large. To your question, Richie. Right, but it only, maybe a particular input only requires a single part of the model to respond, and then a different input comes in and requires a different tentacle of the model or a different expert in the model sense to respond to it. And therefore, when you're training, you're still training a large model, different tentacles. But at inference time, maybe you don't need all the experts to respond. You only need a fraction of the experts, and therefore the total computational cost at inference time is significantly lower.
Okay, actually, I really like that analogy. Yeah, so
I think maybe you're being gracious, right?
Yeah. All right, mixture of octopus models is the next generation.
I'm gonna pay for that, man.
All right. So one of the aspect of, at least creating large language models that seems expensive is that after you've trained it, you need to get some sort of feedback from humans on whether or not it performs well. So it's doing this reinforcement learning step. And then whenever you involve humans, I guess things get expensive. So is that technique going to stay around for a while, or are there ways to avoid having to use humans?
There are several alternatives to that, although I think the jury is still out how accurate they could be. So people use, there is a notion of AIF when you use not human feedback, but you use AI feedback. So if you have a smart model which has been already trained, you can use that to help you to align your new model. There are also techniques like direct preference optimization, which doesn't require human feedback either. So I think community is looking for other ways how to avoid or minimize involvement of human feedback, but jury is still out there of which ones are the best and if we can get away with without any human feedback at all.
I'll say maybe more generally, right? Like reinforcement learning with human feedback is basically one way to get a pre-trained model to behave the way that a developer wants it to based on some optimization function, right? We're all building models to try to get them to do something. And currently, there's a pretty wide portfolio of methods that a developer can use to help the model achieve better output, right? More accuracy for a particular task, right? So there's methods like fine tuning. There's methods like reinforcement learning with human feedback. There's methods like DPO and ROAIF, like Natalia mentioned. There's also building models that are augmented by specific databases, right? Retrieval augmented generation, or RAG models. So a bunch of different ways that people can take a model and basically help it be more accurate for a particular task. And they don't all require humans, but a lot of the models are serving functions for humans. So often when you're sort of measuring a model's performance, you want that human feedback in there. But certainly there are a lot of methods that don't require sort of rich, interactive, time intensive human feedback like RLHF. And coming back to this discussion about compute, right? Like, if you're building a new model, which recipe you choose or which method you choose to both train your model and then make it work really well for your application, it's not as though there is a specification someplace that just tells you, if you're an enterprise application developer or an ML researcher, that, like, if you have problem X, use method Y, or collection of methods Y to build this model. We're really learning that as a community as we go right now. And I think one of the things that's really powerful about having the right high performance AI computing platform underneath, as Natalia and her team, who do solutions engineering with some of our customers at Cerebras know very well, is the value of that high performance engine underneath the hood is that you can try a lot of different methods, right? You can try training a model from scratch, or you can try taking an open source model and fine tuning it. You can try doing other methods like retrieval augmented generation or RAG or DPO, right? You can try these and you can iterate very quickly because you have a fast engine underneath the hood, even for these compute intensive problems. And so, what Natalia and her team has seen with our customers is that this combination of sort of new methods and wanting to build models that are accurate for a particular set of domain specific tasks is being able to iterate really quickly, both at large scale and small scale, with different data representations and different techniques, and quickly move not to just building a model, but building the right model for your application.
Okay, yeah. So I guess it sounds like building a great large language model, or probably anything with AI, is very much an art form. And so rather than just like a procedural thing, so he's got to have that agile workflow in order to test a lot of different things in order to get something that's great.
Yeah, and we were chatting a little bit about this before. I mean, there is definitely an art in the sense that it's evolving, and I think involves a lot of creativity. But it's actually becoming very much a scientific process, right? So testing something and then learning from that test, developing a hypothesis, testing it, and going back. So being able to quickly iterate, like I was mentioning, with different data sets or different hyperparameter settings or large models versus small models, that's, I think, what gets people to really proficient and accurate models for their specific application. But that's hard on traditional systems.
Yes, definitely. If you happen to wait for hours or days to get the results of one sort of experiment because things are running too slowly, then it's not going to encourage you to do lots of different experiments.
Exactly. And it was, I often joke about this, but sort of like that, if it takes you, a couple of days or a week to train your model, in grad school, maybe that's okay, right? Because then you go like for a ski weekend, or maybe take a little vacay, right? Or work on another project. But if you're building a model to help predict optimal drug combinations for cancer, or if you're building a model to help, say, detect fraud in time series data for financial transactions, or if you're building the next great chatbot to improve customer service or retail engagements, and that's part of your core business, like, waiting doesn't work. And so the development velocity is really important. And so, yeah, I think that's what's really driving the field forward. And that's, back to your first question, I think, why we're really excited about pushing into the next 1, 2, 10, 20 years and seeing what people will build given the right tools.
Absolutely. And so I'd like to talk a bit about this sort of business side. I mean, you mentioned time to value is incredibly important. I guess like the $1 trillion question is like, how do I do generative AI cheaper? I think there's a lot of chief financial officers pushing for this right now. So I guess maybe we'll start with companies that have some kind of generative AI in their products and they're doing inference. So what are the sort of main things companies can do in order to reduce the cost of inference?
I think to start, building the right model, right? There are ways that, given a particular inference platform or given a particular performance target, you could choose to train a larger model or a smaller model that will have, say, higher accuracy or lower accuracy, but also higher cost or lower cost. And so step one is think about the business problem that you're trying to address. Think about what the performance metrics are that matter in terms of, say, responsivity or latency, throughput, how quickly a model can answer questions or how quickly your model needs to answer questions and how accurate it needs to be. And then build the right model for just that. I think what we're seeing right now is a lot of enterprises are starting on their generative AI journey by just taking, say, a general purpose pre-trained model from open source and like giving a shot with that. Or maybe trying a third-party proprietary model that's available through a service and giving that a shot. And they're using that to test the value hypothesis and figure out like if a generative AI solution will help them drive revenue or drive efficiency. But then after they get past that initial value testing process, what we often see at Cerebras is enterprises coming and saying, yeah, we tried a couple models, and now we would like to build a model that's purpose-built for our application. You could still start with an open source model, but maybe fine-tune it on my own company data, right? So that the model is really tuned for my application. And we work with enterprise customers regularly every day to help them build models that are purpose-built for their application, including thinking about the right size to optimize inference performance and cost in production. So that was a long-winded explanation of step one, build the right model that fits your application in your inference performance and cost envelope. The second step, of course, is once you have a model that works, deploy it on an inference platform that delivers the performance that you need inside the cost envelope that you're targeting. And as I mentioned earlier, we're really excited at Cerebras to be announcing very soon the launch of Inference on our system. Still uses the big chip, right? So same hardware. In fact, all the attributes that I talked about this chip earlier that benefit it for AI training are also benefits that unlock literally GPU impossible performance at inference time. So we're going to be launching Inference on our systems very soon, and it's going to be 20 times faster than GPU and at about a third of the cost. So build the right model and then deploy it on the right hardware.
Okay, when you say it like that, it sounds so easy. Build the right model, deploy the right hardware.
It's been a great chat. Thank you, Rich. Yeah. Yeah. It's definitely not that easy, and Natalia will definitely knows this better than I do.
Yeah, I just wanted to kind of not only build the right model and use the right hardware for the inference, but also decide from the get-go which hardware you're going to use for inference. And if you want, at the end of the day, to optimize for as cheap or as less expensive inference as possible, that's likely also mean that you will have to invest more into training. But you can save later on inference.
Andy, you mentioned that sometimes like you're going to care about different metrics. So sometimes you need something that's really low latency, so you get quick responses. Sometimes you're going to care about high performance. Can you just give me some examples of like different generative AI applications where you might care about like one thing or the other, and like what might have a different price point, or like how do you go about deciding this sort of stuff?
Yeah, absolutely. So let's talk about latency and throughput, right? Latency is like how long you wait. Throughput is how fast the answers come. And maybe just two really simple examples. One example is, let's say, a conversational chatbot, right? And there, latency and interactivity is quite important, right? Throughput is definitely important too, because how fast, say, the words print out is important. But latency is very important because you're seeking interactivity. On the other end of the spectrum might be a batch offline use case, maybe where somebody has, for example, built a very large, complex model that does things like try to simulate how well particular candidate drug molecules might work on a particular disease, right? And they may be searching tens or hundreds of thousands or even millions of different candidate molecular drug designs against a particular disease. But they can do it offline, and they're not trying to be interactive with it. There, throughput really matters, because let's say that it takes me 6 months on a traditional machine to parse through those, hundreds of thousands of compounds. If I could do that not in 6 months, but in 6 days or 6 hours, then my ability to iterate and go faster and find the right solution to my problem becomes dramatically faster. So that's just an example of where like a latency specific or a latency intensive application versus a throughput intensive application. What's becoming really exciting these days, though, in language models, is not just language models that power conversational chat, but language models that power things like software coding and these so-called agentic models, where you might have a conversational language model front end and then several agent models that go out and perform different tasks. And for those applications, it's not just latency that matters, it's really overall throughput, because those models are processing a lot of data very quickly to, say, generate a new software program or go out and perform some complex multidimensional task with many agents. So with our solution, right, going, say, 20 times faster on throughput, not only opens up far more responsive chat, getting us past this dial-up era of internet into the broadband era of inference AI, but it also opens the door to new language model inference applications beyond just conversational chat, to some of those more complex multi-turn or multi-agent inference applications, as well as inference for far larger models, like multi-100 billion or even trillion parameter models.
Okay, so I think the term large language model is going to become sort of obsolete at that point. Giant language model or something like that. Enormous language model. I'm not sure what the term is going to be, but it sounds big. Okay,
I think you got it. Enormous is pretty good. Yeah.
Okay. So just to summarize what you're saying, I think like the idea is that if you've got chat in your product feature, then you're probably going to care about latency, because humans aren't going to wait a long time for a response. And if you're processing lots of data, then throughput is the thing that you care about.
Yeah, maybe another way to think about that: chat with one single person, how fast the model is responding, or can you afford chatting in parallel with thousands of people? And what's more important to you? The throughput is being able to chat with thousands of people in parallel. Latency is that being really quick in responding to one single person. It'd be great if you can do both of those at the same time.
Just thinking about like a podcast with 1,000 people, that sounds terrifying.
Well, that's why we're going to build a digital twin of you, Richie, so you can parallelize yourself and do many podcasts in parallel.
That does sound fun. So I've had previous guests telling me that podcasters are about to become obsolete by AI, because I'm going to be replaced by a bot. But I like that idea better. Digital twin of Richie is doing thousands of data framed episodes in parallel.
Well, you can ask digital twin Richie to perform maybe the podcast that you didn't want to do as much, and then you can dive into the ones that you really care about.
I thought you were going into reinforcement learning, where digital twin and actual Richie are talking to each other and getting better and asking questions.
Next episode.
Okay, yeah. I'll try and throw that together. All right. One more thing I want to touch on is so I came across this idea of the centralization decentralization pendulum, where computing keeps sort of switching backwards and forwards between stuff that's happening in the cloud and stuff that's happening locally on your own computer. At the moment, like a lot of generative AI services, they're cloud based. Do you think that's going to persist, or do you think it's going to swing back to having local hardware?
I think it's all very intertwined with the requirements and progress. I don't think on the training side we will move anywhere soon to decentralized training. Yes, I think there are a lot of works on federated learning and how to make it work with a very large network of independent small devices. But all of the models which are trained today, it's not even cloud. It's a very special partition of the cloud. And if we are serious, all of the really fundamental foundational models, they are trained on on-prem hardware or on part of the cloud which will have been carved out and specially designed, specially connected. So you can think about that as a very, very centralized beast. So I think training will continue to require these a lot of centralized, extreme exascale compute resources. For inference, it's more tangible to envision that inference will happen on smaller devices, and we can potentially see that decentralized. And with all of the techniques that we talked about, this quantization is easier to apply after the model has been trained. Things like distillation, things like speculative decoding, things like there are, I think, many more ways how to reduce the cost of inference and how to make it work on smaller devices compared to training.
Okay, so we're a ways off sort of training GPT-5 on our own laptops, but maybe some sort of inference is going to be local.
Yeah, and there may even be some very small scale local learning that happens on a device, right? Like maybe maybe some learning about personal habits or preferences on device. But I think Natalia's exactly right. The compute requirements for sort of primary model training today is happening on huge dedicated clusters that are really built for that purpose.
Okay, nice. All right, so before we wrap up, I'd like to know, what are you most excited about in the world of AI? Natalia, do you want to go first?
I think I'm the most excited, again, about all of those use cases which we don't know yet about. And when people ask me where AI can be used, my answer is usually everywhere, because I can fantasize application of AI in every vertical, in every industry, everywhere. But to me, the most exciting when it's not a fantasy, but when it's really implemented, and when there are things real which we cannot even imagine today. The richness of applications and what can be done with this technology in the future is the most exciting. And I believe that AI will change the world very significantly. It will become either much, much better than it is today or much worse than it is today. I'm an optimist. I hope that we'll be able to handle that, and our kids will live in much better world, and we will have things like personalized medicine. We'll all live longer, and we will be working on what we like to do, and we won't do any boring tasks anymore.
No more boring tasks. I like that. And yeah, the goal is sort of widespread adoption of AI and a better world. That does seem that's very utopian. I like it. Excellent. Andy.
It's hard to top that, right? I think
bring some reality.
Yeah. Look, I think large scale AI has this massive potential, right, to transform the way we make decisions, the way we live and work. One of the cool things about working with Cerebras, given the nature of our hardware being the highest performance training and inference systems in the world, customers tend to come to us not with just tiny problems, not wanting to make sort of incremental advances on existing solutions, but they tend to come to us with these really grand and ambitious world-changing ideas, right? We have customers like GSK using and building fundamentally new AI models to accelerate drug development for human disease. We have customers like the U.S. Department of Energy who are building large and small models alike that are new foundation models for science to better understand physics and biology for things like energy generation and the environment. We've got customers and partners like our big strategic partner in the UAE, G42, that are building fundamentally new language models in non-English languages that will reach a far broader population of the world and expand the population of inventors and users of AI systems. And also building models for, say, fundamental new models for medicine and healthcare, right? So I think the sort of enterprise opportunity to build new models to improve revenue and efficiencies in business are huge and transformative in themselves. But I see this untapped potential that if we give people the right tools, and we're Cerebras, we're tool builders, right? We're building computer systems that other people build upon. Given the right tools, I think we have an opportunity to unlock the potential in all those really, really exciting domains. And back to the beginning of our conversation, right? We're scratching the surface today of what people can do. And so I can't wait to see what the next generation of developers builds on systems like ours, as well as sister systems in the cloud, and sort of begins to unlock that potential across enterprise and public and social good applications. It's gonna be exciting.
Okay, excellent. So I think, yeah, definitely going for one-upping Natalia there. So yeah, we're just going to change healthcare and the environment and science and everything. All right, nice.
I mean, but it is. I think there is this huge opportunity to unlock that utopia that Natalia was mentioning. And I think we are optimists, but we're also pragmatists, right? We know that in order to achieve that optimal outcome, we need to give people the right tool. We need to build the right tools so that we can not just build these sort of exciting new applications, but we can also figure out how to do that in a responsible and safe way. I know we didn't talk a lot about that today, but you don't just need high performance compute to build the right model for your application. You also need a high performance computing platform to research different data set mixtures and different techniques to make sure that these models are not just accurate, but they're also responsible and safe and built on an energy efficient platform. So all these factors come together. I know we don't have time in just today's conversation, but I think building the right infrastructure underneath all this is a really important part of not just unlocking those new methods and applications, but also doing that in a way that preserves safety and responsibility and allows folks to do this in a cost efficient and energy efficient way.
All right, nice. So both very utopian visions. I'm very excited about this. There's lots of good stuff to come, and I think that's where we more or less started the show. So I think that's where we'll end it as well. Thank you so much, Natalia. Thank you so much, Andy. It was great chatting to you both.
Thanks, Richard. Really appreciate it.